Grande parte da história da matemática é feita por gente anônima. Anônimos do passado e do presente que se debruçam sobre desafios e quebra-cabeças na busca obstinada pela resolução. Tenho aprendido que a matemática é inesgotável e que o que vamos descobrindo são como pequenos tijolos de uma construção cujo fim é imprevisível. Contudo, algumas pessoas tiveram um papel fundamental no desenvolvimento do que conhecemos como matemática e ciência. Sem suas descobertas, nosso entendimento sobre o universo e o funcionamento das coisas possivelmente não teria progredido. E a história registrou alguns dos nomes e a trajetória de alguns desses matemáticos brilhantes. Mas quem foram eles? Qual sua principal contribuição e por que devem ser lembrados? Há um elo indissociável entre o desenvolvimento da civilização e a apropriação dos conhecimentos matemáticos. No Ocidente, o resgate da matemática ao fim da Idade Média deve-se em grande medida ao comércio da Europa com o Oriente. E uma figura em especial se destaca nesse momento: Leonardo de Pisa, o filho de um mercador italiano que teve contato com a aritmética vinda do Oriente e percebeu que os algarismos arábicos eram mais práticos do que os romanos, até então usados pelos europeus. Fascinado com o que aprendera, decidiu viajar ao Oriente para conhecer de perto a matemática elaborada pelos árabes e gregos. Leonardo se tornou o maior matemático de seu tempo e colocou a Itália na rota das grandes descobertas. Seus estudos vão da geometria à teoria de números e sua influência permanece até hoje. Seu nome original é pouco conhecido, mas seu codinome está cravado na história: Fibonacci. Na Europa, se inaugurava um novo capítulo da história da matemática, escrita por verdadeiros gênios.
And something important happened in the mid-14th century, which was beginning to look at the mathematics of motion. The whole idea of velocity as a number appears for the very first time in the 14th century, but the idea of treating velocity as a number, just as a number without regard to what was causing it or what terminates it, but just looking at velocity as a number. And this would play an extremely important role when we get into the 17th century, the early 1600s, and Galileo. And Galileo never really gets sufficient credit for his contributions to mathematics. Galileo, as I think everybody knows, believed in that we had a solar-centered universe, that it's the Earth that travels around the sun rather than the sun that travels around the Earth. He's really the first person to take a telescope and turn it on the heavens and reveal that a lot that was believed about the way the heavens operate just wasn't true. But he ran into a fundamental problem. If the Earth does spin on its axis, if the reason that we see a day go by, the sun rise and set, is not because the sun is going around the Earth, but because the Earth is spinning on its axis, well, that means that a person on the equator is moving at over 1,600 kilometers an hour in order to get completely around in one day. And even worse than that, if the Earth is traveling around the sun, they had a pretty good idea, a pretty accurate idea of how far the Earth was from the sun. If the Earth must complete one entire revolution around the sun in 1 year, it's got to be traveling at over 100,000 kilometers an hour. So how is it that we're on this globe spinning at 1,600 kilometers an hour and racing through the heavens at over 100,000 kilometers an hour, and we have absolutely no sense of why we are moving so fast? And Galileo realized that if he was going to convince people of a sun-centered universe, he had to be able to explain motion.
Galileu Galilei foi um filósofo da natureza, astrônomo e matemático italiano que viveu nos séculos 16 e 17 e fez contribuições fundamentais para a ciência. Os cientistas da época eram chamados de filósofos da natureza, e a princípio, Galileu se preparou para ensinar filosofia aristotélica e matemática. Contudo, seus estudos sobre o movimento o levaram a divergir das noções de Aristóteles, e isso lhe custou o isolamento dos colegas e a cadeira na universidade que lecionava. Mas, a partir desse distanciamento, ele resgatou as ideias do matemático grego Arquimedes, provocando uma ruptura no sistema de pensamento.
Galileo's great insight was to go back to the scholastics of the 14th century, their treatment of velocity as a number, and realize that that had to lie at the core of how we would explain this mystery. And Galileo very famously said that the key to understanding the universe was mathematics, that at its heart, it had to be mathematical.
Da Itália, a matemática se estabeleceu em solo francês e revelou nomes como René Descartes e Blaise Pascal. Descartes fundiu a álgebra com a geometria, o que deu origem à geometria analítica, e batizou com seu nome o sistema de coordenadas. Já Pascal fez inúmeras contribuições para a matemática, física, filosofia e literatura. Na matemática, talvez sua contribuição mais influente seja o desenvolvimento da teoria da probabilidade, indispensável para a economia e ciência atuarial, que analisa os riscos e expectativas.
So Blaise Pascal was a French mathematician, a physicist, a philosopher, a theologian. He was kind of a jack of all trades, right? He had many hats on. And he introduced many fantastic things, not only in physics and mathematics, but there's one object in particular, mathematics, that we tend to really appreciate, and that's Pascal's triangle. And so what Pascal's triangle is you begin with ones, but then you follow the rule that each number is the sum of the two above it. So 1 and 1 gives you 2, and 1 and 2 gives you 3, and 1 and 3 gives you 4, 3 and 3 is 6, 3 and 1 is 4, 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10. So you start noticing there's some symmetry going on. Seems to be some kind of order within this. But then you can ask, okay, why is this so interesting? Why are mathematicians impressed by this? Well, when you start looking at the triangle, a number of patterns begin to emerge. For instance, you could sum up the numbers in any row. If you sum up the number in the first row, it's just 1. Or in the second row, 1 plus 1 is 2, or 1 and 2 and 1 is 4, 1, 3, 3, 1 is 8, 1 plus 4 plus 6 plus 4 plus 1 is 16. Do you notice the pattern? It seems like each time you're just timesing by 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, and sure enough, it continues in this way. Times 2 is 32, times 2 is 64. And so there's a way in which somehow just adding up numbers is giving you this powers of 2. But there are many other patterns within Pascal's triangle as well. For example, if you look at the first row, it's just ones 1, 1, 1, 1, 1. If you look at this next diagonal, it's counting 1, 2, 3, 4, 5, 6. You look at the next one, what are these numbers? 1, 3, 6, 10. Well, those are the numbers that make triangles. You can have a triangle of just size 1, a triangle of size 3, a triangle with 6 dots, or a triangle with 10 dots. And so each row has some interesting mathematical, each diagonal has these interesting mathematical properties to them. And so Pascal was discovering these properties and discovering these hidden relationships within mathematics. But what Pascal also did is he reflected on the nature of faith and the nature of reason. And Pascal asked the question, are faith and reason, are they in conflict with each other? And Pascal observes a number of things. For instance, he notices that there are two extremes you might fall into. One extreme would be to refuse to use your reason, to not reason at all. But he notices there's an opposite extreme, which is to only use reason. And so Pascal would say things like, there are matters of the heart that reason knows nothing of, right? And he notices that even when we reason, that reason takes us to limits beyond which it can tell us nothing. And so one of the roles of reason is to teach us that there are some things that our reason cannot tell us, that there are limits to reason, and we must exercise reason within those limits, but realize there's a need for something more.
Mas na Alemanha e na Inglaterra, dois prodígios contemporâneos mudaram de uma vez por todas a história da matemática, da ciência e do pensamento ocidental. Seus nomes? Gottfried Leibniz e Isaac Newton.
An entirely new mathematics that finally came to fruition in 1687, when Isaac Newton published his Mathematical Principles of Natural Philosophy. It's generally referred to as the Principia, his mathematical principles. And he beautifully answered Galileo's concern. But what Newton discovered was that gravity doesn't just work on the surface of the Earth, it actually extends out. And he discovered that he could use gravitational attraction to explain the motion of the moon, why it takes exactly as long as it does to go once around the Earth. And if there is gravitational attraction from the Earth to the moon, that makes sense that there's also gravitational attraction from the sun to the Earth. And so Newton was able to explain the motion of the moon, the motion of the Earth, the motion of all of the planets in terms of gravitational attraction that was not just gravity on Earth, it was gravitational attraction between any two bodies. This insight, perhaps surprisingly, was not well received. About 50 years earlier, René Descartes had tried to explain why we don't sense the motion of the Earth. And he did it in terms of an ether that surrounds us and pushes things around. He was going very much back to the old way of thinking where nothing moves unless there is a mover, something that's actually pushing it. And so he postulated this mysterious ether that was pushing the planets around and holding us in place on the Earth. And this is Descartes. People believe that if René Descartes said this is the way it is, then that must be the way it is. But eventually people began to catch on that in fact, Newton really had discovered something important. Very famous phrase in Newton's Principia is, I frame no hypotheses. And it comes near the end of it, after he's done his critique of Descartes. And he realizes that people will criticize him because he's not explaining how gravity operates. He says that there's a gravitational attraction, but he doesn't even pretend to explain how gravity actually acts, how it's possible for gravity to work from the sun on the Earth or from the Earth on the moon. That was one of the big things that people complained about in his theory, and he said, I don't know. And that's one of the most beautiful things he ever did, because at that point he could not possibly have explained it. it took Einstein to explain how gravity really works. And so Newton satisfied himself with laying out the mathematics of it without actually trying to explain the physics, if you will, of gravitational attraction.
Leibniz e Newton viveram na metade do século XVII. Se interessaram e se dedicaram a estudar diversos assuntos. Leibniz era filósofo de formação. Newton era astrônomo, teólogo, alquimista. Ambos contribuíram grandemente para o avanço do conhecimento na matemática, física, teologia, ciência e para o embrião da tecnologia, como no caso de Leibniz, que refinou o sistema binário, que tornou-se a base de todos os computadores digitais. Dentre as muitas ideias revolucionárias que ambos tiveram, uma em especial mudou a maneira de entendermos o mundo em mudança: o cálculo. A partir do cálculo, foi possível dizer precisamente a velocidade com que algo se move num instante particular. Mais do que isso, o cálculo torna possível lidar com leis físicas em geral, não apenas casos particulares mais simples. As mudanças no mundo natural podiam ser agora calculadas e previstas, desde a órbita dos planetas ao movimento dos fluidos. Por incrível que pareça, Newton e Leibniz descobriram o cálculo quase ao mesmo tempo e sem que houvesse comunicação entre eles. Esse episódio gerou o que talvez seja a discórdia mais notória da história da matemática. Quem foi o primeiro a descobri-lo? Mas se a matemática fosse apenas algo que nossa mente é capaz de imaginar, como duas pessoas distintas, em lugares distintos, descreveriam a mesma coisa de forma tão similar? Haveria no mundo natural um fio condutor, uma série de constantes, leis imutáveis escritas no alfabeto universal que são gravadas na natureza, ainda que não houvesse o ser humano para discerni-las?
The period of the Enlightenment, the 18th century, was a time in which this mathematics of motion took on incredible importance. One of the great figures of this time was Leonard Euler, perhaps the greatest mathematician who ever lived. His output was just phenomenal. He worked in all kinds of areas. I mean, he designed hulls of ships, and he explained how objects interact when they bounce off each other, and movement of air, and movement of water. And he's also impressive because the last years of his life, at least his last 15 years, he was totally blind. But he continued producing as much mathematics as he ever had. He simply dictated it. He did it all in his head, and had a pronounced influence on how we understand mathematics and the power of mathematics. He really showed how to take the mathematics of motion that Newton and then Leibniz had developed and show how it could be applied to all sorts of questions about the way in which the world works.
In addition to being an incredible mathematician, Euler, he invented graph theory. He made major advances in number theory and analysis. He's revolutionized mathematics. He was also a pretty good physicist. He studied optics and mechanics and made revolutionary finds in physics. But in addition to that, he was a devoted Christian, and he had a high view of Scripture. And so it really bothered him that he was living at a time when a number of free thinkers, they were called, an atheist movement, were beginning to question the claims of Scripture. And he was particularly bothered with the arrogance that they seemed to have. They were so confident that they could just dismiss anything supernatural. And so Euler would write about this in his letter, a series of letters he wrote to a German princess where he was explaining physics and mathematics. He expressed some of his concern over this. He said things such as, when we study the natural world, so often we find that we can be wrong. And we need so much humility. Doing mathematics and doing physics, it introduces the need for humility. And if that's the case for studying the natural world, how much more in studying the supernatural, when studying questions of not just the universe, but questions of God. We need to come with a humility. And for Euler, the ultimate humility was recognizing we can't know about God unless God reveals himself to us. The only way that we can know what God is like is not by thinking really hard, but by seeing, has God revealed himself? And Euler was confident that God had revealed himself in Scripture. And so Euler had a very high view of Scripture. Every day he would read the Bible. And so while he was doing mathematics, he was also studying to better know the mind and the will of God for his life.
But it was not Euler. It was a French mathematician, D'Alembert, who actually did one of the most important, found one of the most important results of this period, which is to show how this mathematics of motion could be used to explain overtones in a vibrating string. Now, that may sound interesting, but that mathematics turned out to be critical. This whole idea that you could use mathematics to explain overtones in a plucked string, and the way plucking it changes the overtones that you're going to get. This is an idea that was picked up in the early 1800s by Joseph Fourier. And Fourier was studying heat and transfer of heat. And he realized that the mathematics that D'Alembert had used to explain overtones in plucked strings was exactly the mathematics that he needed to explain how heat travels through an object that's being heated. Well, that's very strange because you don't think of heat as having overtones, but in fact it does. And throughout the 19th century, as people continued to build on this, they found that this mathematics of a plucked string and the ability to predict the overtones was coming up in everything people were looking at in terms of physics and in terms of the physical world around us. And the most important example of this is in the 1860s when James Clerk Maxwell in England was looking at the phenomenon of electricity and magnetism. And by this time, people realized that you could use an electric current to magnetize a piece of metal, and you could use changing magnets to actually generate an electrical current. And the challenge was to find the mathematics that would explain what's going on here, how this is working. And Maxwell was the first person really to pull the mathematics together to explain electricity and magnetism. But the amazing thing is that when it all came together and he saw what he had, he realized that he was looking at exactly the mathematics of D'Alembert and vibrating string. That electricity and magnetism is vibrating and sending out these vibrations at the speed of light. And these electromagnetic vibrations, at first, people thought, well, that's just a mathematical fiction. Okay, the mathematics works out, but it's just the mathematics. But the beauty of this is that these electromagnetic vibrations are what today we call radio waves. They are how we communicate today without the use of wires. Nobody would have guessed at the existence of radio waves if it hadn't been for the mathematics that James Clerk Maxwell came up with in 1960 that showed that these electromagnetic phenomena were just like a vibrating string, sending out these vibrations into the world around us.
As revoluções do século XVIII, que elevariam a França e a Alemanha a uma posição de destaque no âmbito político e social, foram alavancadas por mudanças na corrente do pensamento. O iluminismo propunha um conhecimento alicerçado tão somente na razão humana, e a solidez de raciocínio fornecida pela matemática caía como uma luva nesse contexto. Mas foi a Alemanha que viu nascer o último grande mestre a transitar com propriedade por todas as áreas da matemática e por todas as suas descobertas e prodígios. Carl Friedrich Gauss foi chamado de o príncipe da matemática.
One of the greatest mathematicians of modernity, right alongside Euler, is Gauss. Now Gauss, he proved the fundamental theorem of algebra, he revolutionized geometry, he made significant contributions in number theory, like almost every field of mathematics he touched in some way. But Gauss recognized that there are some things more important than mathematics. For instance, he noted that there are many topics, ethics, man's relationship with God, these big questions that are far more significant than any mathematical question. And so he recognized that there are limits to mathematics, that mathematics can only tell us so much, and that there are other questions, much more significant questions, but questions that mathematics cannot touch. The power of mathematics is because we're limited in the kinds of things we think about. We don't ask the huge questions about who is God or what ought I to do. We simply limit our attention to questions of logic, questions of number and relationship and pattern. And because we limit our attention, we're able to produce wonderful results. But you shouldn't go thinking that it's going to be the same way with these other questions. We might need other ways of thinking, other ways of knowing to engage some of those other questions.
Talvez isso se explique pois não apenas Gauss, mas também os demais expoentes da matemática percebessem que algo maior e mais perfeito se revela através das grandes descobertas que permitiram o avanço do conhecimento humano sobre o universo que nos cerca. Tementes a Deus, eles sabiam que algo sempre escapará à compreensão humana. Algo que nem mesmo a mais lógica e racional das ciências é capaz de anunciar. Pois ao perceber a presença do divino, o que resta ao humano é o indizível.